This recording is made in 2025 using the PowerPoint that was presented when Angelo Gavezzotti received the True Blood Award from the American Crystallographic Association at Salt Lake City in 2007. Congratulations again, Angelo. I'm going to talk about serine and atomic force microscopy and a cellular automaton. Here's Angelo. Angelo, as you may know, is an artist crystallographer. I'm the proud possessor of some of his artwork, like this one of a snowy Italian street, which I think is really nice. He also, of course, is a crystallographer. One of his early publications is an artistic one, where he illustrated the 17 two-dimensional space groups with nice figures, like this one, or this one. There are 17 of these. I don't know if you've seen them, but they're certainly worth studying. So he's very interested in how crystals come together, artistically as well as computationally. Now he puts other things together as well. This is Albizzate, Angelo's hometown, as seen on his HO scale train layout. Here you can see it's quite detailed. Here are the townsfolk waiting for the next train. Here's a little workstation with tracksmen and a man loading lumber onto a train car. And here is Angelo's family's apartment, with Angelo on the balcony. Angelo was not the first artist crystallographer. I suppose there could be a lot of argument about who was the first. One of my favorites, as some of you know, is Robert Hooke. I think Micrographia from 1665 is perhaps the greatest scientific book ever. There are chapters about crystals, not surprisingly. Here's sand in urine. He speculates about how great it would be if you could figure out something that would dissolve the sand so you didn't get stones. And here's the very first realistic picture of snowflakes. And down beneath is ice on urine. It was cold in the 17th century, so there's a layer of ice on the urine. But if we go back to the previous chapter, observation 13 was of small diamonds or sparks that you find in flints. There's a scale here. And he notices that the shapes arise only from 3 or 4 several positions or postures of globular particles. If you have 3, you put them this way, 4 this way, 5, 6 you could put several different ways. As for larger numbers, there are various other patterns. And he went on to generalize. There was not any regular figure which I have hitherto met withal that I could not with bullets imitate, even almost by shaking them together. So it's interesting how crystals construct themselves. I designed to get as exact and full a collection as I could of all the differing kinds of geometrical figured bodies. Having such a multitude of instances to compare, as in the solution and crystallization of salts, we cannot but learn plentiful information of the principle which nature has made use of in all inanimate bodies. Incidentally, that's the first use of the word crystallization in Micrographia, and according to the Oxford English Dictionary, the first word of the use of the word crystallization in the English language. And he goes on to provide a mechanism of growth of everything, not just crystals. It starts with fluidity, so a liquid. Then orbiculation. It begins to congeal and get round. And then fixation, it gets hard. Then angulization or crystallization, so you get facets. Germination or ebullition, vegetation, plant amination, sensation, and the highest level is imagination. Hooke wasn't the only one who thought about how crystals were put together. Of course, later on, Abbe Oe dropped a valuable piece of calcite. He saw the pieces were all the same shape. So he wrote this essay on a theory of the structure of crystals and included the first idea that there would be unit cells that would stack up so you would get things like this. And you can imagine putting such things together to get facets and certain angles and different shapes by stacking things together. But is that the way they actually go together? How do you put the pieces together in crystals? How do crystals grow? So a lot of people thought about this, including our friends at the Weizmann Institute, Leah, Mayer, Les. You know their classic from 25 years ago now about RS serine. There are a bunch of serine crystals. The P21 on A space group has a screw axis. So if you have a molecule oriented this way, you also have a molecule oriented that way. This has nothing to do with how they're packed together, just what orientations must be there. And because you have a glide, there must also be enantiomeric orientations like that and that. So these are the orientations. And what they pointed out so importantly was that if you add threonine impurity, which has a methyl group in place of one of the hydrogens, only one of the orientations could be incorporated on that face, but would then stop at the next layer after it was already sealed in there, so it would poison growth on that face. And this orientation would do the same thing on the bottom right face. So these faces wouldn't grow, and you get shapes like that, where the growth is up and up to the right and left and straight down, but not down to the right and left. And similarly, if you put in the enantiomeric threonine, it would have the mirror image effect. And if you put them both in, they grow as diamonds. So that's really an elegant bit of work. If it related crystal morphology to molecular orientation alone, not to how the molecules actually pack in the crystal, but just to their orientation. So one wonders, how does packing relate to the nitty-gritty of growth and dissolution? We can look at a serine molecule here, a reference molecule. Here it is with sticks. It participates in 8 hydrogen bonds with neighbors. Notice there are 4 hydrogen bond donors, the ammonium group and the OH. And there are 4 hydrogen bond acceptors. The carboxylate group accepts 3, but also the OH. Most of the polar interactions are left of center, so there's a polar side to the molecule here to the left, and a less polar side on the right. There's a screw axis here. This is a strong screw axis because you have lots of hydrogen bonds holding the molecules together along there. On the other side, there's also a screw axis, but it doesn't form as many hydrogen bonds. You have a strong screw axis and a weak screw axis. How about the C translation neighbors? There are no H bonds between them. In fact, as it will turn out, these molecules are repulsive. They're only held together by the H bonds to common neighbors. so their direct interaction is repulsive. And then you have the last two hydrogen bonds to glide neighbors on adjacent planes, nearer and further from the viewer. The hydroxyl group accepting from the ammonium nearer the viewer, and the ammonium donating to a hydroxyl further away. So here we have a whole layer of molecules that are related by the screw axis. They're all the same handedness, either R or S. So let's think about what possible ledges there could be in such a layer. You could have a ledge that cuts these hydrogen bonds. That would be easy because it's the weak screw axis. Or adjacent to it, you could cut twice as many hydrogen bonds. That would be hard, the strong screw axis. So obviously you want to cut the weak one, the green one, not the strong one. We think about ledges in other directions. You could cut this way. That's intermediate. Or that way. That's the same. Or you could cut along here, which has a certain number of hydrogen bonds per unit distance that you're breaking apart. So the question arises, what will determine the morphology of ledges you make by dissolving such a thing? You can imagine creating these diagonal things, a mesa coming out toward you, or a pit down in that has this diamond shape. Or you could use some of the other possible cuts as well to make an hexagonal, or maybe pentagonal, or maybe pentagonal pointing the other way, or maybe a rectangle, or maybe some weird shape like that. So the question is, what's going to determine which shape you get? People talk about a layer attachment energy, or in 2 dimensions, row attachment energy, and say you could break where the energy is weak. Then there are questions about how solvation or polarity will affect things. And you wonder whether is this surface polar along the B-axis. And yes, indeed, you see that every molecule has its carboxylate pointing down, so the thing is definitely polar, and that could be a factor. How about the C-axis? Is it polar? Well, from one row to the next, there's alternation in the way it's pointing. But the molecule that goes one way is on the surface layer, and they have their ammonium groups out toward space, while the ones that point the other way have the ammonium group pointing back into the crystal. So they're not really equivalent. So the layer really is polar in that direction, and that could give rise to a difference. So is there a molecule by molecule mechanism in which you get A, then B, then A, then B peeling off? Or do they just sort of come off without any particular pattern? So let's first think about whether the dissolution rate should be determined by row attachment energy. Suppose you have this particular ledge. You wonder whether you're just going to lift this row off or take it molecule by molecule. Suppose you made it molecule by molecule, left to right. To take that molecule off, you need to break 3 hydrogen bonds. 3 hydrogen bonds, 3, 3, 3. Now suppose you do it the other way. To get started, you have 2 hydrogen bonds to break. But now 4, 2, 4, 2, and so on. So it's different in the 2 directions. Let's think about the rate-limiting step for peeling molecules off. if there's a mechanism like this where they come off one at a time. If you're talking about the S-configured chain, it would dissolve rapidly toward plus B, where you've got 3, 3, 3, 3. If you try to come the other way, it would be much slower because you have slow, fast, slow, fast. So it's not the same thing. So there's a lesson here that for a fixed overall energy, a smooth mechanism should enjoy a kinetic advantage. So try to make all the steps as even as possible rather than getting the same overall energy by going high-low. So it's not just the attachment energy, but whether that attachment energy can be partitioned into steps, all of which are fast, that's going to determine how fast something comes off. We studied dissolution and growth of serine by atomic force microscopy. By we, I mean Josh Baraban, who had just finished his BS/MS in our lab at Yale in 2006. This is a picture in Jerusalem. He did some of his work at the Weizmann Institute. Incidentally, in 2024, as Associate Professor of Chemistry at Ben-Gurion University, he won the Israel Chemical Society's prize for Outstanding Young Scientist. I'll give you just a couple examples. The first had to do with the critical size of a pit on a serine crystal. Josh scratched the surface here to make two new pits. A large pit, 2 layers deep, and a smaller pit, another layer deep. With time, the broad layer dissolves, enlarging the larger pit. But the smaller pit fills in. So one was bigger than the critical size, and the other smaller than critical size for dissolution. Okay, so we can observe the critical size. Or more properly, a critical size, because the critical size varies with temperature and solution concentration. This sensitivity makes it difficult to measure absolute rates by AFM. But we can measure relative rates of different ledges. It's not absolute kinetics because we don't know precisely what the concentration is, we don't know precisely what the temperature is. At least we could look at several ledges moving and see which one moves faster than the other. And over very small submicron distances, the concentration gradients, we hope, aren't too big from one ledge to another. Here we have 5 monomolecular layers going down. The highest is the brightest, and blue and orange denote enantiomeric layers. Remember, there's a glide plane here, R, then S, then R, then S. So we have R layers and S layers from top to bottom. So these are high mesas of R serine, and this main plane is S serine. Here's a pit with an R bottom, and down to the left of it another S, and so on. As dissolution continues, the R mesa on the right dissolves away. And the orange S plane is dissolving, which means the blue pit is getting larger. And the remaining R mesa shrinks. And dissolution continues. Josh scratched a little more here to make a new pit. now more than 8 monomolecular layers deep. And continued to watch the layers move. Here's a summary of the ledge movement. We start with a pit, the bottom of which is R-serine. The walls are S-serine. So as S-serine dissolves, we see more of the blue pit. Here are the successive layer borders. So you can see that the top edge moves very fast. That one fast, then medium, slow, and very slow. Now, how about the mesa that was there? It's also dissolving successively. We see that one edge dissolves fast, another medium, and another slow. So those are the rates at which these ledges move on dissolving either the S-serine, the orange, or the R-serine, the blue. It's interesting that glide symmetry obtains. If we look at the rate arrows, by moving across from the left to compare, we see that the rates are the same according to glide symmetry of the planes. Now, at first you'd say, fine, that's what you'd expect. But there might be a difference between a pit and a mesa, because a corner on a mesa should dissolve really easily. It might be hard to remove a molecule from the corner of a pit. So the fact that glide symmetry obtains means that the corners must play no crucial role favoring or inhibiting ledge dissolution. It must be things happening along the edges. Okay, now can we make sense out of the AFM results in terms of some sort of model? What can we learn from it? Can we hope to find the mechanism of crystal growth? Is it hopelessly naive to dream that at least some aspects of crystallization dissolution might become as predictable as copolymerization, for which there are very good A, then B, then A, then B kinetic schemes? If we only knew all the species that are important in the reaction scheme and their rates. If we think of crystal growth and dissolution as a reaction scheme, what would the species be that participate? The species would be surface molecules or vacancies with different constellations of neighbors. Each of these should have some certain rate at which a molecule would come off, some rate of vacancy would be filled for a given solution concentration. And if you had an approximate set of all such rates, you might be able to refine an initial guess to get the behavior you actually observe and learn something about what these rates are. But you need a plausible initial guess. We would need to guess plausible rates on and off for these different constellations. Incidentally, notice this is a structural model. I'm not talking about diffusion gradients, which of course enter in, but we're hoping that for AFM's near equilibrium measurements over a submicron range, this is not a big problem and could be handled later if necessary. One could imagine treating crystal growth from solution with a cellular automaton. You have a grid. Every piece in it has a pair of off and on rates, depending on its environment. So it's exactly a game kind of situation. Lattice replacement by an environmental rule. It's slightly different from some implementations because it's probabilistic. It's not certain that the next cycle will succeed. It just has a certain probability, but there's no problem implementing that kind of thing. I'm told that the first person who did this was Stan Ulam at Los Alamos. Here he is demonstrating what made it possible to do that, this maniac computer. In fact, notice that this cover of Los Alamos Science dedicated to him shows one of these games. He actually worked on crystallization and dissolution, but of course on metals and such very simple structures. Since then, many have done such things. That's why kinetic Monte Carlo was invented. Graham Henkelman in Austin did simulations of silver and copper crystals with distributed processing, where he sent it off to many computers because it's a big problem to do that. We didn't do anything that sophisticated. We were sort of the children's crusade. Here I am as Peter the Hermit, leading some good students off to bondage in the Levant. But they are very good students. One was Tom Gniadek, who worked on this as a senior and continued to work on it while he was in medical school. Incidentally, Tom is a wonderful and very smart and able guy, but wherever he went in his rotations in medical school, in cancer or orthopedics or wherever you go, they always had him work on computer programs, for good reason. I did too. The other was Josh Baraban, who did both the experimental AFM studies and applied the programs Tom wrote. These are both wonderful, wonderful students. What kind of assumptions go into this kind of simulation? Well, the kinetic scheme must neither be impossibly complex nor experimentally underdetermined. If there are just a zillion parameters that are important, we're never going to be able to deal with refining them to fit experiment. It's important that there be a smallish number of relevant neighbors of any kinetic significance, not ones that are out 3-unit cells. There must not be really, really drastic surface reconstruction, because we want to have surface sites be relatable to the bulk crystal lattice. We need adequate computer speed to simulate a surface area, something like what we can observe with AFM. As of 2007, we were limited to just 2 monolayers, R and S, and we had to ignore diffusion. There should be a limited amount of arbitrary tweaking of the parameters, with some rationale behind it. Finally, you have to have a plausible starting guess. That's where our honoree comes in, because Angelo is the world's expert at selecting relevant variables and useful approximations. So we wrote to him and asked if we could have some idea of what the energies are for all these various neighbors that you have in a particular constellation. Here's the scheme for using Angelo's stabilization energies. You have a piece that's going to come in, and Angelo can tell us the energy. Of course, we're working in a solvent, not gas phase. If it turned out that the solvent-solute interactions per unit area on the left were the average of the solid-solid and solvent-solvent on the right, then it would be neutral. But probably they are not. If the interaction is solvophobic, you should have less stabilization before addition than the average. So what are we going to do about this with Angelo's numbers? We said, let's suppose there's a scaling factor that we scale down because we have these solvent interactions there. This can't be right. They're certainly not uniform. But we take Gavezzotti's numbers and scale them down. I got an email from Angelo when we started this. He said, one thing is knowing energies. The other is estimating attachment or detachment rates. How do you go from an energy to a rate constant? That may very well be a second-year textbook question, but I don't seem to have a quick answer. So we need the activation energies. The problem is there's going to be transition state desolvation. So as a preliminary guess, let's suppose that that's roughly proportional to the bonding strength. Of course, it's not uniform, but we've got to start somewhere. So we'll assume that that's also some fraction of Gavezzotti's energy, a fixed fraction. And then there's something about how much flexibility, sort of an entropy thing. So let's just suppose that's proportional to the exposed area. So we have this really crude guess of what the rate on should be, a concentration factor times that, and the rate off. So we just need these two numbers, A and EG, and scale with the factors S and F. The most important is EG, the Gavezzotti energy. Angelo sent us this sheet with his numbers. There are 8 near neighbors of the highlighted central molecule, 4 pairs involving interactions A through E. The strong screw with H bonds C and D, only one of each pair is shown. Each member of the pair has a total favorable energy of 118 kilojoules per mole. The weak screw, B, each with a total favorable energy of 74 kilojoules per mole. The A glide to the adjacent layer involving H bond A and favorable energy of 78 kilojoules per mole each. And the C translation, E, with no H bond and a repulsive energy of 16 kilojoules per mole each, primarily because of Coulombic repulsion. With these 4 pairs, that is 8 neighbors, we have 2 to the 8th, that is 256 possible constellations, many of which would certainly never occur, like having just one neighbor, especially if it is repulsive. So the question is, how many of them are kinetically important? Whether there are few enough that we can meaningfully refine their rate constants. We do this by running a simulation. Okay, so the first thing you do is adjust the concentration so the lattice doesn't just fill in randomly or wildly dissolve. So on this particular laptop, in a minute, I did 26 million trials, decided in each trial whether the step succeeds by its rate being larger than a random number. After 26 million trials, there were about 43,000 molecules lost, but about 41,000 added. So a net loss of 1,800. But the shape is what's important. It doesn't look anything like what we see by AFM, which was a queer kind of pentagon that just goes off at a funny angle. So then the problem is to adjust key barriers, keeping the equilibrium constants that we scaled from Angelo, but changing the barriers. That's pretty constrained. To see if we can do better. How do we know which rates to change? Consider a hypothetical case, beginning with someone's scratched initials. Using our initial rate guesses. Here are the first molecules to be lost irreversibly, color-coded as to the constellation at the time of loss. As time goes on, we record the constellations for the last loss of each molecule. Remember that most losses are reversed, but the last one limits the rate. You see that a smallish number of different colors of different species are determining the pattern formation, more like 2 to the 5th power, that is 32, than 2 to the 256th power. And on any given ledge, very few are relevant. So these are codes for different environments and where they occur on ledges or corners. And here's how much we changed them in what I'm about to show you. We retarded 12 of them to the red values and accelerated 12 of them to the green values. And in order to get anything reasonable, we had to change one equilibrium constant by a factor of 3. After making these few changes, we started with a hole like that in a field of over 1,000 unit cells, 1,000 by 1,000. So lots of molecules, that's getting up to about a micron. So it's getting in the range of what we can do experimentally. Last night, I took 20 minutes to do 268 million trials, in which about 500,000 were lost, and 500,000 were added, for a net loss of 58,000, which developed into this shape. What I was trying to do was match this shape, which Josh had observed by AFM. So there's the simulation. It's not quite right, and with Josh and Tom, my last research students, gone, I was unable to follow up. You may need more neighbors, more than just the very nearest neighbors, in order to get all the features that Josh's movie showed, but it's pretty promising, I think. So the question was, can we find the mechanism of crystal growth? And the answer is yes, but someone needs to carry on from Josh and Tom to find it. So we thank Paul Hansma, who got us into AFM, and Dick Miller from ONR, who provided money, and Jen Swift, who started us in this kind of stuff with AFM, and John Gultz and Po-Ching Chen, who started work on serine. Craig Stephan also worked on it, and Mayer and Leslie, and Leah, of course, and especially Angelo. And I'll just close with this quote from another email from Angelo. Ludwig Kernen was famous because he was rather stout, and when bending over the table to read a papyrus from close by, he used to unlock his belt and undo the zip of his trousers for more ease. He also had a famous German accent. When speaking of the U.S., he said, "To think that this country considers beer an alcoholic beverage." Congratulations, Angelo, and thanks to you.